Hello everyone, this is Hiba Khalidi from Certara speaking, and I'll be providing you with a demonstration of SimRFlow and all of its different modules, starting with the data collection module, where we collect physchem data from a wide range of user-selected databases like Chembl, PubChem, and EpiSuite, which we get it from the Norman suspect list, and also PK data, which we get from the httk-r package or can be user-provided. All of this data is collected and passed into the various Simcyp PBPK models that can simulate all of the various compartments of the human body. And we use that using the Simcyp R package. In this case, it's going to be version 23 of the Simcyp R package compatible with version 23 of Simcyp, both of which are the most recent versions of the Simcyp simulator. The compounds are simulated in high throughput, one at a time, producing database files. This happens in a matter of seconds. The database files are stored and they contain all of the compound-specific profiles and parameters, which can then be tapped into or accessed also using the Simcyp R package to provide all of those different visualizations. So this is what I'll be showing now, the different modules: data collection, simulation, and data visualization. You may find additional data and resources about the Simcyp R workflow both on my GitHub page, which I update regularly and push new updates with the most recent advancements and modifications to the workflow, and also on the original paper, which has a very extensive supplementary materials that explains how you can use it on your own device if you have access to the Simcyp simulator. This is SimRFlow's R-Shiny app, and you can find it on the GitHub page. As you can see, it's comprised of the three modules: data collection, simulation, and plot visualization, where the simulation here has two sub-modules, which I'll get into throughout this demo. You can see here a box prompting you to upload a CSV or Excel file. And if you hover over it, it tells you the main headers or the most essential headers that must be present in your CSV or Excel file before you upload. This is an example of a CSV or Excel file that you would be uploading as an input to SimRFlow. It has the mandatory headers over here, the compounds, their respective InChIKeys, and a unique code for each compound. Headers that are not at all necessary for SimRFlow and so would therefore be neglected or not looked at by SimRFlow at all. And then finally, optional headers like dose, where you would like to provide different doses to simulate for the different compounds. Other optional headers would include the dose units and the method of prediction for the steady-state volume of distribution. But this is what the input file would look like, and other input files like experimental data would look very similar to that. More information on that is found on the GitHub page. So I'll upload an exemplar compound file, to which, as you can see here, immediately it detects the main columns of interest, especially the InChIKeys, since they will be used to query the databases for the data that we want. And here I've got an optional one, which is called dose. In this case, I want to simulate the different compounds at doses that are different from each other. So I don't need to finish a simulation, reparameterize the model with a new dose, and then run it again. Instead, it's all run in high throughput. I'm also here given a prompt to select which databases I want to query for my physchem search. It's going to query Chembl by default, but I can choose to either query PubChem or the EpiSuite database, which I can uncheck if I don't want to query them and only want exclusively Chembl data. In this case, I'll query both of them. The code that I've written to query those databases uses and relies on APIs, which makes them much more portable to use, as you don't need to download a large SQL database or a large database in general and carry it around with you. All you need is an internet connection, and you'll be able to access all of the physchem data you need using those APIs. So this is what we're getting over here: the polar surface area, hydrogen bond donors, compound characterization, pKa's, basically everything that is required, physchem-wise, to run the Simcyp simulations. I'm also provided with a list of compounds here in the red box which have not been found. These compounds could be completely missing, as in the InChIKey did not match with anything in PubChem, Chembl, or EpiSuite, or they might be compounds with missing essential information like log-P or molecular weight, without which they cannot be able to be parameterized within the Simcyp simulator. For that, you can upload additional physchem data, if you have it, by conducting your own literature search and then incorporating that into the database. In this case, I'll just go ahead and allow my SimRFlow not to simulate those. But then I can go to the next step of the data collection, which is the experimental data curation, which entirely relies on the HCTK database. Now, I'm using only 3 of the databases within HCTK. There are much more than that, OBAC, WAMBL, and the in vitro database, all of which contain different parameters of interest, like the fraction unbound, hepatic intrinsic clearance, and the blood to plasma ratio. And I might be getting multiple fraction unbounds from the different databases, to which I need to either get an arithmetic mean, geometric mean, medium, or choose the minimum or maximum if I'm choosing to be conservative or not too conservative in my assumptions. The same applies to Clint. I might be getting 2 different Clints from the different databases, like the in vitro database and WAMBL. What do I do with those? I can choose whichever is more suitable for my purposes. And then I can search the HCTK databases. You have an option here that says provide experimental data. In that case, let's say you have your own experiments that you've conducted and you want to supply them to SimRFlow to use them in the simulations. You can do so by checking this box and then uploading an experimental data file which has those headers: code, blood to plasma ratio for BP, fraction unbound for FU, and Clint. In this case, I don't have any experimental data to upload, and I've got my experimental data over here. So if I scroll over here, you'll be able to see that some compounds did have fraction unbound values in the HCTK database, and I've calculated the standard deviation if there were multiple values associated with that, and it gives you the source exactly. And this applies to other parameters like blood to plasma ratio and Clint, etc. That wraps it up for the data collection module. The next step would be the Simcyp simulation modules. The first being the prediction module over here that allows you to predict parameters like the fraction unbound, steady state volume of distribution, blood to plasma ratio, and the dissociation constants. All of this is very high level. You just run it without actually running the simulation. You just get the high level predictions before you run the simulations. And this could be informative when you want to compare that across a large number of parameters. So this might take a few minutes. A few moments later, we've got the predictions for all of the compounds of interest that we've simulated over here. It was the 40 or so compounds, and it took less than a minute to do so. And you can download that as a CSV or Excel file. The next step is the human simulation, where you access and use a Simcyp PBPK model of the healthy human person. You can adjust a lot of things with that. Of course, you provided your doses, as you can see over here in your inputs. You've got different doses for the different compounds and the different dose units that you've selected over here. But let's say you want to use multiple dosing instead of single. You just switch the radio button over here and you can set a different number of doses and a dosing interval, which could be every 12 hours. And of course, if you change the simulation duration, you can have multiple dosing and a set dosing schedule. Very basic scheduling, but it allows you to see the accumulation of the compounds if that is what you're interested in seeing. You can specify some additional subject parameters. Of course, it's in a healthy human population and it's going to be on adult humans, neither pediatric nor geriatric, so the range is from 18 to 65. So you can narrow down this range if you're interested in a very specific age group or make it as wide as you want. And of course, if you want to test your compounds on different proportions of male or female populations, it could be all male or all female population. You can set the female proportion over here. The administration route could be oral, IV bolus, or dermal. And if you select dermal, you have some additional parameters that you may set regarding the application or the dermal exposure of your compound, like the formulation thickness and the area of application. So let's stick to oral and set the number of subjects to 5 and the simulation duration to 24 hours. And the steady state volume of distribution prediction method, of course, you can set that based on the different compounds that you have. So we leave it up to the user to select whether they want to use prediction methods 1, 2, or 3. All of it is dependent on the compounds that they are using and what they prefer to have. Of course, if they want to have different volume of distributions for the different compounds, they can add an additional column similar to the dose column called VSS, and it will have or be able to run in high throughput the different steady state volume of distributions. For renal clearance, we offer the mechanistic kidney model or a very simple fraction unbound multiplied by GFR altogether. And it shows you here the inputs that you're going to pass into the Simcyp simulator to run those simulations, including your physchem parameters that you've collected from the different sources, as you've seen previously, and the other PK parameters that we've collected from the HTTK R package. If I click simulate over here, concentration time profiles were going to be generated, and a summary of the simulated outputs are also going to be generated. This will take also a couple of moments as the simulations run, and I'll be back to show you them when they're ready. A few moments have passed and we've simulated all of our 40 or so compounds over here, and we've got the simulations in all of the different tissue compartments: brain, gut, liver, spleen, kidney, etc. Everything that we need to look at in our concentration time profiles would be there for all of our PPK compartments. And this is downloadable as a CSV or Excel file. We also have the summary of the simulated outputs over here, which is a high-level view also of all of the data that we've generated, like the various Cmaxes and their standard deviations, AUC, Tmax, half-life, accumulation index. All of those parameters are here for all of our compounds, and some additional population-specific parameters like the body surface area, age, body weight, GFR, etc. So all of this data again is downloadable as a CSV or Excel, and you can use that to make whatever plots you wish to make. Which takes us to the third and final module of SimRFlow, which is the plot outputs. Under plot outputs, immediately the first thing you'll be able to see are the concentration time profiles, and we've set that to have multiple dosing with 2 doses, 1 every 12 hours, and you can see that over here in the multiple dosing options. 2 doses, once every 12 hours for a total of 24 hours, and this is exactly what we see: a spike in the concentrations once every 12 hours with a termination at the 24th hour. We've got all of our compounds that we wish to visualize. Different compounds will have different concentration time profiles, and we're looking here at the brain, but we can look at other parameters, for example, other tissue types, like the skin, for example, the plasma. All of those are going to have different concentration time profiles, and we can change the concentration units from micromolars to nanograms per milliliters. As you can see, the number changes in the y-axis over here. Indeed, we have 5 subjects as we've specified, and we see the profiles of all 5 of those subjects. But we might be more interested in seeing the mean of those subjects and their 95% confidence intervals, in which case we can change the plot view. And this applies to all tissue types. We can look at liver, for example. We can see the liver concentration time profile, the mean concentration time profile, and its 95% confidence interval. We can look at the y-axis, so the concentration, either in a natural scale or a logarithmic scale, whichever is more suited for the purposes that we are looking at. Sometimes you want to have a full overview of all of the different tissue concentration time profiles for a given compound, and you can select the all tissue type, in which case you will see all of the 12 tissue compartments that have been simulated for that compound over the time range that has been simulated, and you can look at it in a natural scale. Perhaps it's clearer that way. But in a sense, you get a very high-level view of what is happening, and you can take a look at the different Cmaxes or the maximal concentrations that have been reached in the different compartments. Perhaps you can see where the compound reaches the most or where it reaches the least, and that would be good to keep in mind when you're doing things like risk assessment. So this is what it looks like for the concentration time profiles aspect. We can also look at the parameter distributions and relationships. The first being distribution plots over here, which are basically density plots, where the x-axis would be the parameter of your choice, and you can choose from a very big list over here. These include population parameters, simulated parameters, and sometimes even the input parameters that you have provided, like fraction unbound, if you've collected that or provided that. But you can see here the range over which the spread looks like. You can see if your distribution is normal or uniform, etc., or if it's skewed to the left or to the right, and some aesthetic changes that you can adjust over here. With relationship plots, you can select what goes on the y and the x-axes, and it returns here a correlation coefficient r, which tells you perhaps the extent of the strength of the relationship between the different parameters. Now, whether this gives you meaningful conclusions or not is entirely up to you, and of course, the results for that would be stronger if you have more subjects, so you'll have more of those scattered dots around, and the line that would go through them would be more clear, and the relationship would be stronger. Sometimes there would be no relationships between the parameters, but you can choose whatever goes on the x and y axes. In this case, we can see that as body weight increases, the plasma Cmax also increases, and I can switch the positions of those on my plots over here. So we can make body weight the x variable, so as body weight increases, we see an increase in plasma Cmax. Maybe that is not for sure, we don't have enough points to make that conclusion, but this is what the data shows us so far. We also have the cross-compound comparison charts. Now, these charts would be very dense the more compounds you have, because you'd have a lot of those bars. But maybe you're taking a look at plasma Tmax and you want to see which of my compounds has the highest plasma Tmax. So I can order it in ascending value over here, and I can see compound 26 has the highest plasma Tmax. If I want to order it in terms of compound code, it would be in alphanumeric ordering over here. But I can take a look at any of my parameters. Some parameters have extremely high volume of distributions. I might flag this parameter as there seems to be an issue with this specific parameter, so I need to go back and take a look at its data. Finally, we have the physchem properties versus predicted parameters. This allows you to bridge the gap between the data that you've collected in the data collection module over here and the parameters which have been simulated. In this case, we have the compound characterization as the physchem parameter over here, and then we've got the plasma Tmax as the y parameter over here. It could be Cmax, it could be really any other parameter. And you can see, for example, monoprotic acids seem to have a very wide spread for the plasma Cmaxes, whereas diprotic acids are very constricted into a very narrow region, or we simply have not enough diprotic acids in our sample. But really, we can choose any of those physchem parameters to be on our x-axis. We can put log p. Is there a relationship? There doesn't seem to be a relationship here between log p and Cmax, but again, we have the correlation coefficient r here to give us a more informed view of this. But yeah, this is what it looks like, and these are the different data visualization options. There's a help tab over here that has some additional information on how you can use this tool, but all of the information is on the GitHub page and in the supplementary materials. And thank you so much for listening to this demonstration. I hope it was useful.